Okay, guys. So today we're going to learn a little bit about nuclear decay and nuclear chemistry. Before I even begin, I'm going to let you know that this is a little challenging. So I do not expect you to fully grasp it just from this video, but I do want you to try as much as you can today to try to do the best that you can. And then we'll talk about it a little more tomorrow. But first, of course, we're talking about nuclear chemistry because this unit is all about looking at the nucleus. So we're only going to be focusing on those protons and those neutrons. So nuclear chemistry, as it says here, is the study of reactions that are caused by a change in the nucleus of an atom. This change has nothing to do with the electrons, only the protons and neutrons. Review, because this is really important after your quiz. What happens to an element if you change the number of protons? I'm going to give you a second to think about it. Okay, so remember that the number of protons tells you what element it is. If you change your number of protons, you change your element. So for example, with nitrogen is N, it's number 7 on the periodic table. If you're looking at nitrogen, it has 7 protons. If you add a proton to nitrogen, it now has 8 protons and it's oxygen. If you subtract a proton from nitrogen, it now has 6 and you have carbon. So if you change your protons at all, you're changing your element. Remember, if you change your neutrons, it doesn't necessarily mean that you have to change your element. So there are six big ideas that are going to go along with the chemistry notes for nuclear chemistry. Your first one, the purpose of a neutron in the atom is to make the element stable. Remember that neutrons can change. That's where we have isotopes. And every element on the periodic table, well, most of every element on the periodic table is going to have an isotope of some sort. And a lot of times, some of them are going to have multiple isotopes that can be stable. But sometimes you're going to have isotopes that are not stable. And so any atom that is unstable, has an unstable proton to neutron ratio, is going to be considered radioactive. So if you've ever heard of anything as radioactive, this is what they're talking about. Atoms with an atomic number greater than 83 are naturally radioactive, and they have no stable isotopes. So if you take a moment to look at the periodic table, if you look at 83, 83 is Bi, which is bismuth. Little fun fact about bismuth, it's partially radioactive, meaning that it's not super stable, but it's more stable than the ones greater than them. And there is one common household item that has bismuth in it, and you may take it when you're not feeling well. Bismuth is one of the main active ingredients in Pepto-Bismol. So when you're taking Pepto-Bismol, you're actually taking something semi-radioactive, which is kind of cool to think about. Obviously, it's not going to hurt you that much, otherwise we wouldn't take it, but it does help your stomach when you're not feeling well. So if we're going back on track, right, anything 83 and above is going to have be unstable naturally as it is. So they are going to start decaying down to become like an element before number 83. Now there is one exception. The one exception is technetium. If you look on the periodic table, technetium is number 43. You could see on the big periodic table in the room that it's not filled in. And the reason for that is that it's a man-made element. All of your man-made elements are not going to be stable on their own. As soon as they're created, they start to decay. But if you're looking generally at the periodic table, everything up to 83 are going to have at least one stable isotope. Some of them have multiple, as you will see throughout this unit. Any kind of elements outside the band of stability will spontaneously decay to form a more stable element. So if you look on your paper, you have this chart that you have on the board. I want you to look specifically at all the little dots here. Okay, so all those dots. Those dots there are called the band of stability. And the band of stability tells you what is the good ratio of protons to neutrons and what is going to remain stable with that. So if you look here, your atomic number, it kind of fizzles out around 83, which is what we were kind of looking at. And then your number of neutrons are going to also kind of do the same thing, right? So if you look at the beginning, there's a pretty good 1-to-1 ratio. If you have 10 protons, then you're going to have 10 neutrons. But that's eventually going to kind of stop happening, and you're going to start getting a lot more neutrons than protons in order to keep that stable. But one thing that we have to think about is that when an element decays, it's actually getting rid of some material. But we have to keep in mind, before I move to the next slides, we have to keep in mind the idea of the law of conservation of mass. And the law of conservation of mass states mass is conserved in any chemical or physical change or reaction. Matter cannot be created or destroyed, for all particles must be accounted for. Okay, so even though these elements are decaying and getting rid of protons or neutrons or whatever they might be doing, those protons and neutrons still are there, right? They're just now off on their own, as you're going to see in the moment. So no matter the fact that they are also decaying, right? All these elements are decaying, but you're not eliminating protons and neutrons like they have completely gone away. Okay, so here's the big stuff. There are 3 different types of decay. You have alpha decay, you have beta decay, and gamma decay. Alpha decay is going to be your most common form of nuclear decay. And what's going to happen here is that you're going to have elements that have really heavy nuclei. So a lot of your ones over 83 on the periodic table. And so what's going to happen is that if you have too dense of a nucleus, it's going to want to get lighter because it doesn't like to be super dense. Just like we talked about in the stars don't like to have a super dense core because they explode. So if we're thinking about this, right, if you look at your example at the bottom, we're looking at uranium-235. Uranium is at the very bottom of the periodic table, number 92. All right. So what's going to happen with uranium-235 is that it's going to lose 2 protons and 2 neutrons. Remember, protons are positive, neutrons are neutral. Protons plus neutrons give you the mass number. So if we're looking at uranium, its mass number is 235, right? We know it has 92 protons. Go ahead and take a moment to calculate how many neutrons uranium-235 has. So you should have, at this point, calculated, and if uranium-235 has a mass number of 235, and it has 92 protons, that means it has 143 neutrons. So what's going to happen is that it's going to get rid of 2 protons and 2 neutrons. And what we call that the alpha particle, which is the same as a helium nucleus. So if you look at the He at the end of this decay, right, He 4/2, what this is telling you is that you've gotten rid of 2 protons, 2 neutrons. And then you look at what element did I make? Because remember, if you're getting rid of protons, you're making a new element. So if I take 2 away from 92, that brings me down to TH. And TH stands for thorium. Okay, so thorium has 90 protons because we lost 2. And it's going to have a mass number of 231 because you're losing 2 protons and 2 neutrons. If you look at either side of the arrow there, your numbers should match up whether you have to add them together or not. So for example, if we're looking at the left side of the area or of the arrow where it says uranium-235, our top number is 235. If we move over to the right side of the arrow, you have 231, and then you have 4 if you're looking at thorium and helium. We have 231 on the top of thorium and 4 on the top of helium. If you add together 231 and 4, you get 235. This is that idea of the conservation of matter, because we have to show that all of our matter gets transferred. It's getting transferred somewhere. So your numbers on both sides have to match up. And if you look at the bottom, right, if we are looking at uranium again, the bottom says 92. If you go to the right, go past the arrow, you've got 90 and 2. If you add 90 and 2 together, you get 92. Okay, so every time you have alpha decay, a helium nucleus is getting emitted. You're subtracting 4 from the top, 2 from the bottom. Okay. Beta decay is a little different. Beta decay doesn't have to happen necessarily with just your big atoms. This can happen with small. And so what this is when you have too many neutrons within a proton-neutron ratio. And so if we remember, a neutron is neutral. But I want you to think of a neutron as having a positive part and a negative part that cancel each other out, right, to make it neutral. Well, what's going to happen is that one of those neutral neutrons are going to break down.
If you're currently parked in spot number
Hold on just a moment.
67, you need to move your car at this time so the band can practice.
Okay, let's go back to that. So think of your neutron as a positive part and a negative part. Okay, when you have too many neutrons, one of those neutrons are going to break into its positive and negative. The negative part is going to be tossed out of the nucleus because at that point it's basically an electron, right? So an electron is emitted from the nucleus, and that positive part is going to stay and become a proton. And so what's going to happen is that your mass number is not going to change, right? Because we still have the same number, or we still have like a set number, whatever's in there. But your proton number is going to change. So one of those neutrons become a proton. So if you look at the bottom example for this, right? Say we have carbon 14. Carbon has 6 protons, and its mass number for this is 14, right? So that means if we have 6 protons, how many neutrons do we have? Go ahead, take a moment to think about it. If we have 6 protons, you should have 8 neutrons. So one of those 8 neutrons is going to break into its electron and its proton part. The electron leaves, and you're left with a new proton. So if you look, if your protons have increased by 1, you now have a bottom number of 7. 7 on the periodic table is nitrogen. So your carbon gets turned into nitrogen. Nothing happens to the mass number because you're just taking a proton or taking a neutron and turning it into a proton. But you want to make sure that you include the beta particle because whatever your numbers are on the left side, they have to match on the right. So if we're looking at carbon at the very top, this top number is 14. If we look on the right side of the arrow, we have a 14 next to the nitrogen, and we also have a 0. 14 plus 0 is 14. Both sides are equal there. But if we look at the bottom of carbon, carbon has 6. We go over to nitrogen on the right side of the arrow, and it has 7. You somehow have to get that 6 and that 7 to even out. And so that's where that beta particle comes in. Because if you have 7 plus negative 1, what that really means is that you just have 6, right? So 7 plus negative 1 equals 6. Both sides are balanced. I know that's a little confusing. I know alpha and beta decay are challenging. But gamma decay, I think you're going to be okay with. So gamma decay is not looking necessarily at protons and neutrons. It's more looking at energy. And so in any type of isotope, all atoms like to have a lower amount of energy. And so say an atom has a lot of energy, it has a high energy. It wants to decay down to have a smaller energy. And so what it's going to do is it's going to emit a gamma emission, which is just a high energy wave. These gamma waves are really dangerous, and we actually use them a lot in medicine when we're doing x-rays and things like that. But they aren't as common as alpha and beta decay, which are pretty harmless to us as humans. But gamma emissions are pretty rough. So if you look at your example at the bottom, what you're going to notice is that whatever you have on the left side of your equation, you're also going to have on your right side. So mercury 197 is the same on both sides. The only thing you have to do is you have to show that a gamma emission has occurred. And that's where we have this spot right here. So you have those 2 zeros and you have that gamma emission. And that just shows, okay, nothing actually happened to mercury in terms of protons and neutrons, but it did release energy. So keeping that in mind, alpha decay releases 2 protons, 2 neutrons. Beta decay releases 1 electron and it turns a neutron into a proton. And then in gamma decay, nothing's really happening to the mercury other than losing energy. And that's where that gamma ray comes in. So what you're going to do is you're in a moment going to be getting a worksheet. I know this is very challenging and really confusing, and I'm going to have to go over it more with you tomorrow, and that's fine. But I want you to give it your best shot to try to figure out how to answer these questions. There is an answer key, so if you get stuck, feel free to check. That's totally an option. Also, feel free to use a book. The books are in the back of the classroom part over on the black bookshelf, so you can use those to kind of help you work through that. Otherwise, give it your best shot, and I will see you tomorrow.